Thank you. Well, my name is Pablo. I'm going to present the paper Scaling Loss. This research was done along with Hernán Vazquez and Jorge Sánchez in the Mercado Libre research team. For those of you who doesn't know about Mercado Libre is the largest e-commerce platform in Latin America, with presence on 18 countries, 150 million users, and on the last year, almost 400 million items were sold on the marketplace. So, without further ado, let's start with the presentation. I would like to structure it as follows. First, I'll briefly speak about the sequential recommendations problems, to then draw a relationship with language modeling. That will allow us to start to talk about the language modeling scaling loss, and then use that framing to come back to sequential recommendation and establish key differences that need to be addressed. Lastly, we are going to show and discuss experimental results. So what are sequential recommendations? Sequential recommendations arise when users interact with the platform, and we want to leverage that all interactions the user did to predict the next one, and hope that model that predicts the next interaction is going to be good to recommend things to the user. So that looks very similarly to language modeling. In language model, we want to predict the next token from a sequence of tokens, and as I was saying, in sequential recommendations, we want to predict the next action from a sequence of actions. That relationship caused that many breakthroughs on NLP end up translating into recommendations. For instance, word to vec end up being prod to vec, or metaprod to vec, language models with RNN translating in models such as group for rec, BERT into BERT for rec, and maybe we could add this paper to the list, scaling loss for rec. So yes, that's the thing, scaling loss appear in language models, and so the question we ask ourselves is, do recommenders scale as well? So let's do a brief recap on scaling loss of language models. So in a nutshell, it means that more data allows us to fit bigger models that would perform better. And in order to talk about that, we need to introduce another concept, which is the concept of flops budget. So the question really translates in the optimal compute allocation, where given a fixed flop budget, we ask ourselves, how should we trade off between model size and dataset size? So if we look at the literature, for example, the Hoffman paper of the chinchilla, we can see that they train many models, and what they look at is on the x-axis, the flops, the amount of flops, and on the y-axis, the loss function. And we can see this gray dotted line that is the optimality frontier. What's the best thing we can do for a given amount of flops? So for example, if we use 10 to the power of 19 flops, we can achieve a loss value of 3. And if we use 10 to the power of 20, we can achieve something like 2.5. And then we can ask ourselves, what was that model that gave rise to that value? How many parameters, how many training tokens? With that, we can build this table of flops budget, best achievable loss, optimal parameters, and optimal tokens, and start comparing and trying to analyze the relationship between those columns. So, for instance, continuing on the chinchilla paper, we can see that there is a linear relationship on the log scale between flops and parameters and flops and tokens, drawing the conclusion that optimal models for higher flops budgets are larger and require more data. So, how can we test for scaling loss in recommendations? How can we transfer this to them? And in order to do that, we need to analyze two key differences. First, evaluation. Language models are mainly evaluated on loss or perplexity, which is basically the thing we are optimizing for. However, on sequential recommendation, we're interested in ranking metrics such as NDCG or mean reciprocal rank that are not differential. So that's one of the differences. The other difference are tokens. In language model, there are relatively few amount of tokens, around in the tens of thousands, maybe at most 100,000 tokens. They are atomic units of information that do not change over time. However, in sequential recommendations, tokens are items in the single behavior case, and items are redundant since many sellers can sell the same thing, and they contain metadata that are such as title, price, amount of sales, And they change over time, since it's not the same to talk about a scarf on winter or in summer. And in Mercado Libre, for example, the amount of items are a lot more, like 70 million, for example, in Brazil. That alone makes it infeasible or makes a very bad choice to use ID-based embeddings, because on the one hand, we wouldn't have a good representation on the long tail, and on the other, it would be a waste of parameters having an embedding matrix of 70 million times, I don't know, 100 to 100, whatever. So let's try to what architecture did we use. We choose SASREC because SASREC is a very simple architecture. It's basically a transformer decoder. It's basically the same as GPT because we wanted to analyze scalability and not be entangled with any elaborated losses or design choices. And we made two small modifications. The first one is eliminate embedded lookup matrices and use metadata to compute embeddings. And the second one is use sample softmax to optimize ranking metrics, because it's known to optimize them. We named the resulting model Scalable Recommendation Transformer, but again, it's a very small fork on non-architectures. Now, we can finally start talking about scaling loss in sequential recommendations. So our paper in a nutshell can be summarized as follows. We first started with the Amazon review data, the 2018 version, and built 5 different versions at different scales. Then we trained several models varying number of parameters and provided evidence of existence of scaling loss, and finally demonstrated its transferability to downstream tasks. So there's a nuance when we want to scale this kind of data sets. NLP scales with the number of tokens. We just need the model to keep scanning tokens and keep predicting. However, e-commerce scales with number of interactions. And the number of user interactions depends on user, and it would be weird to include some user interactions and not to include them all. So in order to scale the data set, we need to first sample some users and then include all of their interactions, because that is what is going to happen in practice. So next thing. In order to evaluate our model, we use temporal ordering or leave one out, as it's used in literature. And let me do a comment there. Let me do a pause. If we visualize schematically how, for example, 4 users will look in temporal ordering, in this matrix where we have x-axis the time and the y-axis are the users, white cells are nothing, the user did nothing, green cells is training set, blue cells is dev set, and purple is test. So what happens if we know that this day was Christmas? Well, what happens is seasonality. We do certain things on certain days. We buy certain stuff. We visit certain places. So knowing what user 1 bought for Christmas will leak into the test set of user 2. Since we wanted to compare ourselves to the literature, and this is very used, we decided to use it anyway, but we argue that something like using absolute dates to split train, test, and dev is more appropriate. Continuing. So our experimental design can be summarized as follows. We compute 5 different data sets with the methodology of sampling users and include all their interactions. We removed all users that appears in the Amazon Beauty and Amazon Sports data sets because we are going to fine-tune our model there, and we don't want our model to know anything about those users. Then we train some models with different parameter counts. The hyperparameters can be read there, also, of course, in the paper. And we evaluated on NDCG at 5, again, to be able to compare ourselves with literature that is very commonly used, NDCG at 5. And lastly, we fine-tuned and evaluated on beauty and sports data sets. So let's go to the results. If we look on the x-axis, the flops, y-axis NDCG instead of loss, we can see that, as we expect, the value of the NDCG increases as we increase the computation. And in this chart, we added the optimal frontier, what was in the Chinchilla paper, a gray dotted line. This is the blue line. Now we can analyze what happens in the optimality frontier. So if we compare the amount of flops to the amount of parameters and the amount of flops to the amount of interactions, we can see that there's a trend going up. Of course, you might have noticed that there's are horizontal lines in the parameter in the left plot. That's because of the way we did the grid search. Maybe in follow-up experiments, on follow-up papers, we can do something like isoflops that is done in other methodologies. But overall, what we can see is that the best performing models at increased amount of flops have higher parameter count and have higher number of interactions. Moreover, we fit a variation of the function that is used to predict this performance evaluation as a function of number of parameters and number of training interactions. And what we can see is that on the one hand, there is a very similar exponent on both amount of model parameters and training interactions, suggesting that we should increasingly somehow equally, but care must be taken and interpreting this, since this might be affected by these horizontal lines. Anyway, we see that there is evidence here that where we can argue that scaling law exists. So, finally, once we have these checkpoints, we grab one of them, the best for performing for the high amount of flops, and then what we do are two experiments. On the one hand, we randomly initialize the architecture and train it from scratch in order to understand how would that architecture would work on the Amazon Beauty and Amazon datasets. And then we did a fine-tuning to understand how this pre-training translates into results. What we see, thank you very much, what we see is that not only the from scratch version does very decent job, but it is also comparable with some of the papers methods that we use to compare. But when we fine-tune our model, we can see that there is a consistent increase in the performance metric in DCG and HIT-5. So to summarize, as I was saying, we started from SUSREC, we modified it for it to scale, we built scaled versions of the Amazon data, and we validated the existing scaling laws, and finally fine-tuned them to and improve competitive models. All the code for the datasets and the pre-train and fine-tune can be found at the repository with that QR code. You can reach me if you have any questions either on Twitter or on email. Thank you very much.